Welcome everyone. We are making eighth week session. So, so this time I'm missing something from the classroom, which was discussed about solution of system of differential equation. Okay, so I'm leaving that part particularly to recall things. Okay, so if you want to recall that last two section, which is just application of primary decomposition theorem. So you can look into video once more if you wish. Okay, I'm not recalling that part. So eighth week was started with this theorem. The theorem which says let T be a linear operator on a finite dimensional vector space. Okay, and T is diagonalizable. Eigenvalues are given C1, C2, Ck, distinct eigenvalues. Then there are k linear operators, which are actually projections, projections onto uh, eigenspaces. Okay, so even is projection onto first eigenspace. Okay, so T can be written like this: T is equal to C1 E1 plus C2 E2 and so on. And identity operator is just sum of these projection operators. Okay, this is same as saying eigenspaces span V. Okay, second condition implies that even EI and EJ composed composition is zero. Okay, this will imply that actually if you take two eigenvectors corresponding to different eigenvalues, then they will be linearly independent. Okay, so this is third condition. Fourth condition is saying EI is projection, and the range space of EI is null space of T minus EI. This is exactly saying that uh, eigenspace corresponding to Ci is nothing but range space of EI. Okay, so converse is also true in if these condition 1, 2, 3 are satisfied, then he is diagonalizable and fourth and fifth also hold. So there is a proof given in the class. So I'm not going to recall that. Okay. So but these will be certainly helpful solving exercises. Okay. So this is primary decomposition theorem. The statement says if P is a linear operator on a finite dimensional vector space P and P be its minimal polynomial such that P is equal to this factorization P1 power R1, P2 power R2, Pk power Rk, where each Pi is monic irreducible polynomial. Okay, Ri is some integer, positive integer. Let Wi be null space of these factors Pi or Ri of P. Okay, then V is direct sum of Wi's, where Wi's are this null space of Pi power Ri of P. Each Wi is also invariant under T. If T is Ti is the restriction of T on Wi, then the minimal polynomial of Ti is this factor only, Pi power Ri. Okay, so this was primary decomposition theorem. Okay, so next was I'm leaving the application part, but I want to recall something. Jordan nilpotent matrix. What was that? Let me define it. Jordan nilpotent nilpotent block. This was actually super diagonal entries are one. Okay, and all other entries are zero. Even in the diagonal we have zero. Okay, but super diagonal means these entries. Sorry, where I'm writing. This one is enter. So like this, and everywhere else is zero. This kind of matrix is called Jordan nilpotent block. And what is Jordan block? Jordan block corresponding to some eigenvalue lambda, corresponding to lambda. Lambda is an eigenvalue. Then uh, of Jordan block of order R. This is nothing but R cross R matrix, R cross R matrix, where each diagonal entry is lambda, okay, and super diagonal entries like that. This is one, and everywhere else is zero. Okay, so this is Jordan block of order R. So next we have this theorem, which is not proved in the class. It might be proved in coming week, but if you see the statement of this theorem, so we'll solve some exercises regarding these statements. Probably in the coming weeks, you will see the proof of these theorems. Okay. So this theorem, first theorem was if n is an nilpotent operator of order k, its index k means uh, n power k is zero, but n power k minus one. Composition at k minus one times is not zero, but if you compose them k times, then it is zero. Okay. Then n has a block diagonal matrix representation. Okay, where each diagonal entry is a Jordan nilpotent matrix. Okay, then there is at least one Jordan nilpotent matrix of index k, and all others are less than or equal to k. All other blocks are basically not of the same order, or means not bigger order. Okay, one is at least one should be there of k index. Okay, I mean to say if there is, let's say, index of, let's say, index of n is 2, okay, n 2 is equal to 0, then all the blocks in the representation, they cannot be bigger than 2 cross 2. Okay, this is the maximum, or otherwise it will be singleton 1 cross 1 or 2 cross 2. That's all. Okay, so uh, total number of Jordan nilpotent matrix will be uniquely determined by n. Nilpotent matrix is specify the matrix. Okay, and it is some detail, more detail given to it, but I'm leaving this. Okay, because in the coming week you might see the proof of this, then you will see this statement again. Okay, so Jordan canonical representation theorem, this theorem is also not proved in the class, but look at the statement. Okay, T is a linear operator on a finite dimensional vector space, and this F, which has factorization like this, which is characteristic polynomial, and this P, usual notation for minimal polynomial of T. Okay, then T has a block diagonal representation J, such that each diagonal entry is a Jordan block along with these four properties should be in mind. Okay, so for each eigenvalue Ci, there will be at least one Jordan block. Okay, so for each eigenvalue, there is some Jordan block of order Mi. Okay, Mi is this powers coming into uh, minimal polynomial. Okay, so all other blocks will be of order less than or equal to Mi. Good. This I suppose you understood this. And sum of all orders of these blocks corresponding to Ci, this must be equal to Ni. Ni is this powers coming into characteristic polynomial. Okay. So third condition says the number of Jordan block associated to eigenvalue Ci must be equal to symmetric multiplicity of eigenvalue Ci. Okay. So number of blocks appearing into matrix representation, that is actually geometric multiplicity of Ci. Okay. Uh, Total number of Jordan block will be decided uniquely by T. So T has a representation, then number of Jordan blocks are basically invariant. Okay. They might be and miss. There might be situation like if you choose different bases, making it Jordan canonical form. It might happen that uh, blocks are actually permuted. Okay, inside diagonal. So some block diagonal means like inside diagonal blocks can permute. Okay, this is what. But number of Jordan blocks they are invariant to permutation. Okay, so let's see some question, and I suppose we can do this together. E be a linear operator on P which commutes with every projection operator on V. Okay, then let E1, E2, EK be projection operators on V with W1, WK corresponding range spaces of V, range spaces of EIs, then V is linear sum of, such that V is linear sum of these things, WIs, which of following statements are correct. So if you see these linear operators which commutes with EI, so each WI is T invariant. First note that WI are invariant under T because T commutes with each EIs. Okay, and WIs are range of EIs. T invariant under T. WIs are actually the space of V. Okay, don't forget that. Now, first option says V is direct sum of WIs. Is this correct? I'm saying no. Someone give me example. A simple example. In first option, there is no involvement, but involvement of T. Okay, they are just saying WIs are T invariant. That's all. To take T to be identity operator. Okay, and T to be identity operator on R2. Take E1 is equal to uh, take something. Okay, E1 is equal to E1 of X Y. Define it like X comma 0. This is projection onto X coordinate. Okay, for X belonging to R. Take E2 is equal to identity itself. Then E2 is also projection, right? E2 square is equal to identity itself. And E1 square is equal to E1 square of XY. This is nothing but E1 of EX, E1 XY. And this is nothing but E1 of X comma 0. And this This will become x comma 0 itself. Okay. So even just focusing on first coordinates. So E1 square is also projection. E1 and E2 are projection. So do you see counter example? What is range of E1? W1 is x-axis. I mean to say this is just x comma 0 type. What is W2? W is nothing but R2 itself. Okay. So uh, W1 plus W2, this is R2. Means this is V, pura, whole V. But this is not direct sum. W1 direct sum, W2. This is not even defined. Not defined. Since direct sum uses definition that since W1 intersection W2, this is non-zero. Okay. Mhm. Okay. So if else, what about the WIs are invariant undertaking? Oh, this is this note observation. First observation. Okay. If T commutes with S, so kernel of S, range of S, these are T invariant. From that theorem it follows. Okay. How we follow? Let me write it here. If S is equal to ST, then range S and kernel S are T invariant. So is correct. What was third option? Even composite with EJ 0. Not always. You can look here. See from A. Look at A option. If you compose E1 with E2, this is not 0 because this is nothing but E1 itself. Because E2 is identity. I'm taking identity from A. Okay, so this is not 0. So this option is correct. Incorrect. Each EI is projection. This is definition of projection, and it is given projection of it. Okay, so we have two options correct. What is this? This just EI square is equal to EI definition of projection. Okay, so my computer is not working properly, but let me see. Okay, okay, let me go to next page. Everyone understood this, right? This was simple question. No one is listening to me, or I am not audible.
We are listening, sir.
Audible,
Okay, sir. Let me see. Next question. Uh, let P be a space of continuous real valued functions from this interval -1 to 1 closed interval, and WE be the subspace of even functions, and WO be the subspace of odd function. Okay. So what are these? Let me explain this. WO is f from -1 to 1, such that f of x of minus x is equal to minus of f of x. This is odd. For even, this is f, f from 1 here to real. F is function from uh, this interval I to, let me denote I by this -1 to 1 r, such that f of minus x is equal to f of x. This is even function, set of even function. Okay, so what is question? Which of the following is correct? Correct option. So V is direct sum of, sorry, V is linear sum of these things, but not direct sum.
Sir, I have a doubt.
Where?
Sir, in the vector space, there is an element called identity element. Then if we take W1, so W not a set of odd function and W is set of even function, then
Okay.
ide- identity considered as even function or odd function.
This is coming into both because both of these are subspaces. Identity is not decidable, right? It belongs to W also and WE also.
Okay, thank you, sir.
I'm saying given any two subspaces, intersection में zero तो होगा. Okay. Okay.
Yes,
So,
sir.
nothing comes in other than zero. There is no element which is even function as well as odd function. Okay. Something which is even and odd both, that is just zero. Okay. So even if I'm not looking at first this, it is linear sum or not, I'm not saying anything about it. But this is not direct sum. Oh, oh, sorry. This is wrong. This is wrong. I'm saying. You know why? Because uh, direct sum says intersection is trivial, and here it says intersection is non-trivial. Okay. Okay. So this is incorrect.
Could you please, could you please show
Let me
how
explain.
is not trivial?
How is this not trivial? Okay. Let me explain the first option why it is. First of all, any vector v inside capital V is the function this f. Okay. Let f belonging to V. Then write f as f of x is equal to f of x plus f of minus x by 2 plus of x by, sorry, minus of minus x by 2. Okay. Okay. So from here, if you see this function, first part, okay, this is even function. Okay. Let me write it. Let me write it. G of x is equal to fx plus f of minus x by 2. This is even function because this can be written as f of minus x plus f of x by 2, and this is nothing but g of minus x. Okay, so g is an even function. This is even, and this is an odd function. Okay, odd. So every vector can be expressed as sum of even function and odd function. Okay, so first this part is correct. This part is very much correct, but the second part is wrong. I'm saying because something which is even function and odd function together will be zero. Let me explain this part also. I suppose I can do this. Okay. So let f is even and odd both. F of x is equal to f of minus x and f of x is equal to, sorry, minus fx is equal to f of minus x for every x in the domain which is I. Let let me take f to be common inside w intersection w. Then first, because it is even, this condition holds. Because it is odd, this condition holds. Then uh, from these two conditions, you see, uh, subtract first from second. So right side you will get 0 because they have same thing on the right. But this side you have 2fx. Okay, because 2 is non-zero, this will say fx is equal to 0. And this is happening for every x, means every step for every x. 9, fx is equal to 0 for every x in I. Okay, so something which is even and not function together will be zero function only. Okay, understood? Okay, so what about B option? B option says indefinite integral operator. Okay, 0 to x integration of ft. Then wo and we are invariant under T. So let's see about wo, if it is invariant or not. I suppose it should be wrong. So let me see if what about wo part B. Take something in wo f here, and we want to shoot ef belongs to w not, question mark is here. It belongs to w not, wo. Okay. Then wo will be T invariant. But let's say take something f to be sine theta maybe. Okay. If f is sine theta of x is equal to sine x. Sine x is an odd function, right? Okay. Then TF. What is TF? By definition of T, it will be cos x. And this is not in W. It belongs to W. Right? So this way you can show that WO is not T invariant. But I suppose then giving a counter example is best. I know my idea, but that will not be good to you to hear that. But okay, this is a good counter example. Okay, so WO is not T invariant, so this statement is totally incorrect. Even if W is T invariant, I don't care. They are saying both are T invariant. So this is wrong thing. Okay, so this is incorrect. Oh, this was also incorrect. Now let's see part C.
So you are saying it is invariant, again you are saying it is not invariant.
This is not invariant, not T invariant.
Here in the answer you are saying it is invariant.
Because they are not invariant. So this is incorrect. Oh, sorry. It is correct. They are not invariant. So this option is correct. Incorrect. If I say W is T invariant, I'm wrong or right? I'm wrong. I just given counter example. WO is not T invariant. That is the correct option. Okay. So
Oh,
this is okay.
not invariant. When it will be invariant, sir?
When it will be invariant,
Ah,
W is a subset is
yes, yes.
WE is invariant. You know, WE is invariant. Let me calculate WE is invariant. Why? Then you might understand little better. Maybe take any F inside WE.
You take cos x, sir. Given function.
Sorry, there is some mistake here, right? Is there mistake? EF is equal to cos x. EF is nothing but I evaluated at x. Let's say positive side. X is positive for some time. Right now. So this is fx means sin x d 90 dt. Then this will become cos t 0 to x. Oh,
Minus
sorry.
cos t, sir. Minus cos t.
Minus cos. Okay,
Integral
sorry.
sin t is minus cos t.
Cos 0 is 1. I was wrong. Sorry. So there is some mistake, but let me explain other idea which I had.
Sir, here we can
What?
also fx, if we take fx is equal to x square, then its
Yeah.
integration will be the not a even function. Then it is not
Not
invariant, we can say.
x cube by 3.
If you are taking fx is equal to x square, then its integration will be tf will be. This is good. That is why I was saying we should solve it together. Then we will understand better. Sometime I may not get some good example like you get. Okay, so they are taking fx is equal to x square function. So let me write here a variable t square dt. And then it will be t cube by 3 0 to x, and this is x cube by 3. So you see something which is non-zero and even function, and after applying t, it becomes uh, odd function. Is that right? Yes. Absolutely. Yes. So so B option is also incorrect. Okay. Here we have counter example. I think there is some mistake in sin cos x. Leave it. Okay. Ignore it. Just calculate TF at minus x, your x square function only. This will become 0 to minus x t square dt. Let me draw a graph here. Here you have minus x. Here you have plus x. So integration is just this area under curve. So this area is just take minus outside so that limit is in proper direction. Minus here, minus x to 0, t square dt. Okay, so now we are taking from here to here, area under curve. But these two areas are same. So this is nothing but 0 to x only, t square dt. These areas are same. So this is minus of, what is this? Efx. Correct. Good. Yes. So actually we got that tf is not even function. Okay. This is tf is odd function. This is what roll by calculation. Okay. So tf was calculated like this value, and tf of minus x we calculated, and we got tf of uh, okay. So tf is odd function. F we take is equal to x square. F will then f belongs to we, but tf belongs to wo. So this was good counter example. Let's see third option. So E is a operator from V to V defined by this. EF evaluated at x is this. And the range space of E is WO. So they are saying EF is an odd function. That is all. Means EF range space of E is WO, means all set range space of E is what? All collection of EF type elements. Okay. So they are saying that EF is an odd function. Is this correct? Look at here. This part is the actually A explanation for A starts below here. This was general restrictions. This is not an odd function, right? This part we are calling first part only. This is an even function. Here is description for C. So this is wrong. Okay. What about this? They are saying null space of E is WE. Means take any WE element, means even function, apply E, you will get 0. Now you tell me it is correct. B part says fx minus fx minus x by 2.
Then what
This
is the
is your
range space, sir?
range space of what?
No, in the C. Range space of E is W0 is wrong. Then it is WC is answer. Is it answer?
This is wrong.
This is wrong.
Because
Okay.
of this it was wrong. So
Then what
if
will
it
be the
was
range
WE,
space of E?
it will be even functions, right? These are all even function.
Okay, sir.
Here you have explanation.
Okay, okay.
So because of this part, we have wrong. He was wrong. So about D. So for this range space is WO. This
E.
is correct.
WE.
Range space of W. It will be WE. Sorry, WO. Let me explain once more. Sometimes I mess up things speaking. So this is your E defined from E defined from V to V. Okay. So um, what is EF or any F? EF or any F belonging to V. Hmm? Odd function, right? Odd function. So range of this E, let's say E prime. Okay. E prime. Okay. Range of E prime will be range E is nothing but W O. What is null space of E prime? Null space of E prime is nothing but E, because whenever EF is equal to 0, I'm talking about F. Will F be even? Let's see. If EF is 0 function, then Fx minus F minus x by 2 is equal to 0 for every x. Okay. But this will imply Fx minus F minus x is equal to 0. But this will imply that Fx is equal to minus x. Right? This implies that F is even function. But this implies that F belongs to WE. What is kernel? Means kernel space of E or kernel of E prime. This is nothing but WE. Okay. This is just description for that. Okay. So what about D part? D part, null space of E is WE, which is correct. Okay. This PDF will be available. Your voice is audible here. Okay. So
Sir,
Sorry, sir.
sir, sir, in V, f of x is equal to x square. Why can take, sir?
what?
In V
Where?
explanation, f of x is equal to x square. Why can take?
Actually, na, we want to do. We want to disprove these things. Okay. That W is invariant.
Yes, sir.
So we can take any function in WE. So this x square was simplest one. Even x can work. Take x in W naught. Okay. Identity function in W naught. X. Then what will be the integration of it? PF. PF will be x square. So x was odd function and its integration become even function. So they are not T invariant. That's all. You can take anything. Some odd for which after applying T becomes even, or for even after applying T becomes odd. So you can take anything. Nothing is special about x square. Okay.
Okay, sir.
Sir, for this problem, the range space and the null space both are even functions.
Or T, na?
Ah,
Yeah, I was thinking so.
because we want to write it as a range space should be different from null space, no?
No, no. Uh, we are not talking about range space of T, range space of null space of T. That is not given in the question. But you are saying that range and null space both are even functions. That can happen. Right? That can happen. So take function like this. This I'm writing here in the corner. Take function in R2 like this. X comma y goes to y comma 0. Okay. So you see what is kernel here? X axis. what is range here? X axis. It can happen.
In a projection, it can happen, isn't it, sir?
In a projection, this is not projection. Projection with some rotation maybe, or reflection. Yeah, reflection. This is composition of reflection and but it can happen. That is what I'm telling. That kernel and range, they can be same. Like here, kernel of T is equal to range of T. Okay, so here it was the case. I think this was the case for T integration operator. Okay, here also, but that was not given in the question, so we are leaving this. You can check it out. Okay, we have no more page left here, so we are leaving to next question. If you do not understood, did not understood somewhere, then you can ask me, or let's go to next question. To the vector space of dimension 8, T be linear operator on V. Minimal polynomial is given like this. So some hidden factors are here. X plus 2, x minus 2. Okay. Let the geometric multiplicity of 2 and minus 3 be 2. What will be the possible Jordan canonical form? So now the last theorem which I was uh, recalling means that is applicable here. So first of all, look at power. Minimal. This is minimal polynomial. This is 3. So corresponding to eigenvalue minus 3, sorry, minus 1, there should be 3 cross 3 matrix. Okay, 3 cross 3 block. And every other block corresponding to this should be either 3 or less. It cannot be bigger than 3. That's all. So there should be at least one 3 cross 3. So these two options are incorrect because minus corresponding to minus 1, we don't have, we don't have 3 cross 3 third block. There should be at least one. So in these two options, let's verify.
Sir,
So
could you please repeat the thing? Why we conclude that both first two option is incorrect?
since corresponding to lambda is equal to minus 1, we do not have 3 cross 3 Jordan block. This was first thing in the list. If you see here, this there will be at least one Jordan block of order mi. This mi is powers in minimal polynomial. Okay, so here we have that power for minus 1 eigenvalue is equal to 3. Look at here.
Okay,
So
sir,
there
now
should,
it's fine. Thank you.
so first two options are incorrect. So let's see others. Corresponding to plus 2 and minus 2, we should have only 1 cross 1. Okay, but this says that C is also false, right? Here we have power, maximum power is just 1 here also. So we cannot have bigger means order. So only this D option is correct. let me write it here so that next time while you read it, you can understand. So AP false. And C fails. C is false. Why? Since M2 is equal to 1, corresponding to eigenvalue 2, but sorry, this will imply we cannot have Jordan block for 2 eigenvalue 2 eigenvalue. This is notation for eigenvalue uh, of order bigger than 1. We can have order only 1 cross 1, and 1 cross 1 there should be at least 1. That is also given condition. So it is false. So only option D stays. It might be false or all option may be false, but why D is correct? D is correct. So this satisfies first condition. Okay. All others are 1 cross 1 block. Each per there is nothing missed. You say 2 minus 3 minus 2 minus 1. Corresponding to each eigenvalue, we have some block. And because minimal polynomial has powers for this 2 minus 2 and minus 3, only one power. Okay. Look at here 1 1 1. So these are 1 cross 1. This is also fair. So we verified only 1 2. Okay. So this is 3 cross 3. Order sum of orders should be matching with the uh, dimension of V. Okay. So 3 cross 3, 1 1 1 1 1. How many? 5 3 8. Yes. Dimension of V was 8. So while if you write matrix representation, this will be 8 cross 8. First block is 3 cross 3, and all 5 blocks are 1 cross 1. So this is correct. Okay, the option is correct. Verify it. I verified. If you want to go back, you can watch video once more. Otherwise, directly you should verify so that you can next time verify by yourself. Okay. So let's see. Question number 4.
Sir,
EV linear. Okay, Oli.
in the previous question, here is
Yeah.
a given another information about the geometric multiplicity of 2 minus 3 and is 2.
Oh, I missed something. Sorry. So this just says that there should be two blocks for minus 3, 2 blocks for plus 2. That is what is given. Okay.
Okay.
This was third condition. That is also verified now that I was missing. So there are two blocks for 2 and 2 blocks for minus 3. Okay. So if anything left, there were 4 conditions. But anyway, if something is left, you verify it. The fourth condition is nothing. This is just saying uniqueness of matrix representation. So this is good. We understood third question. Let's see fourth question.
Sir, in which book we will find these kind of problems to practice? Please mention. We don't find any books. Only theory part is given in the books. Problem parts for practice we don't find.
I have Joseph Gallian in my hand, but I don't think it has.
Please write down the name of the books, author name. Page number.
So, okay, in this PDF, I will write the name of the book. There are theory books, but
Theory there are
in,
books, but problems we don't find. Problem solved books.
uh, there was a famous book, but I don't remember. Uh, Let me see if I will tell you in the next video, means next week, or in the same PDF or in YouTube channel. There will be a name given for the book. Okay, I don't actually remember this, but anyway, I will answer this question. You will get the book soon. Okay, name of the book soon. So let's see fourth question. Gilbert is trying. Maybe I don't remember. This name I remember. Gilbert or Hilbert. Okay, sorry, Gilbert is trying. Look by this author name. If there is linear algebra book, that is good. Okay, and you can find such questions. There are more examples than theory. Okay, so let's see fourth question. There may be some mistake in the name. Okay, but anyway, uh, TB linear operator on C defined by this. Let T1 be T minus 2I and T2 be its square, T1 is square, T3 be T minus I, T4 be its square of T3. Wi are corresponding respective null spaces of Ti's. T be the minimal polynomial for T. Then which of the following statement is correct? So what is minimal polynomial? First option is saying what about minimal polynomial thing? What is P? So let's calculate. This is calculation. Okay. So first is saying a product of T1 and T3. The product is 0. So what is T1? T minus 2I means 3, 3 minus 2, 1 minus 1, 2, 2 minus 2 minus 1, 2, 2 minus 2. This product with x minus 2. X minus 2 corresponds to T1. X minus 1 corresponds to T3. This is your T3 and this is T1. Sorry. I subtracted 2, so it should be T1. Now I'm going to subtract minus 1. Sorry, subtract 1. 3 minus 1. This is your T3. Sorry. Now it is correct. 1 minus 1, 2, 2 minus 1, minus 1, 2, 2, minus 1. So is this product 0? So let me write matrix once more. 2 has to 1, 1, minus 1, 2, 0, minus 1, 2, 2, minus 1. Sorry, here you have minus 2. If I'm writing somewhere wrong, then you can point it out. 2, 1, minus 1, 2, 1, minus 1, 2, 2, minus 1. The product will be 2 plus 2 minus 2. I'm not going to write everything, okay? Because first entry is not 0. So this product is not 0. So P does not satisfy uh, that matrix T. Sorry, matrix A. So this is incorrect. Uh, Whatever. After calculation, this is not 0 matrix.
Sir,
Okay.
the The theory behind this calculation is that we are trying to find it is doesn't annihilate the matrix.
If it does not annihilate, then he cannot be minimal polynomial, right?
Oh,
That is what theory says. Theory says if P is minimal polynomial, it satisfies P and of minimal degree. That is also important. Minimal degree polynomial which satisfies T. So this calculation which is written here, this is nothing but P of T is equal to this. Or in fact, I'm writing just P of A. A and T they are interchangeably noted down. Okay. So there is a fixed basis, a standard order basis. So you can write P at any time, A at any time. There is a basis behind uh, every representation. Okay. So what about B part? This is A. A fills. What about B? X minus 1, which is this matrix. X minus 1 means uh, this would subtract minus 1 here. So we get 2, 1, minus 1. I'm just writing P of T, which is T minus I product with T minus 2I square. This So this is 2, 1, minus 1, 2, 2, minus 1 here. Now second matrix, which is T minus 2I. The calculation is so long, but you can solve directly taking, if you take characteristic polynomial, I think this is the characteristic polynomial as well as minimal polynomial. Okay, so you can directly calculate what is minimal polynomial now. Why? If you calculate characteristic polynomial, if it turns out that this is your characteristic polynomial, there is this P should divide characteristic polynomial. So this is doing good job. Option A. But option A does not satisfy C. So it fails. So what is 1 degree bigger than this polynomial? This would be the correct thing. Okay, this is characteristic polynomial as well as minimal polynomial. Then. Okay. This is my this is I'm just verifying Cayley theorem. Okay. Cayley theorem. This says that characteristic polynomial satisfies minimal polynomial. Sorry, matrix satisfies its characteristic polynomial. So you can directly calculate characteristic polynomial if you wish. Uh, I think this matrix multiplication will be long, so let's calculate characteristic polynomial itself. Why to waste time here? So determinant of this is your characteristic polynomial. The determinant of 3 minus x, 1 minus 1, 2, 2 minus x minus 1, 2, 2, 0 minus x means minus x only. What is determinant for this? 3 minus x minus x, 2 minus x plus 2 minus 1, 2 into minus x plus 2 minus 1, 4 minus 2 into 2 minus x. Let's calculate it here. 3 minus x, what is it? Minus 2x minus x square here plus 2 minus we are getting here 2 minus 2x minus we are getting here 4 minus 4 plus 2x, only 2x left. So from here if you add them,
Should be 2x, sir.
oh sorry 2x only left. Correct. 3 minus x x square minus 2x plus 2 minus, you're getting minus 2x minus 4x, oh sorry, plus 4x minus 2. Is there mistake? Sorry, 2x get cancelled.
Cancel. 2x minus 2x will cancel. We'll get minus 2.
And we get minus 2 only. Yes. So x minus 1 satisfies this equation, or this we let equal to 0. Or we should expand this and then factoring a polynomial. This is tough job. Anyway, we have to do this. We'll do it. So let's write it here. 3 minus 3x square minus
6x
minus 6x plus 6, right? Minus x cube minus minus becomes plus 2x square minus 2x minus 2. This 6 minus 2 becomes minus x cube plus 5x square minus 8x plus 4, right? One satisfies this. So x minus 1 is a factor. Okay, x minus 1 is a factor of it. You see 5 plus 4 9 minus 8 minus 1 9. So you have minus x cube
Next point. Nina say that.
plus
Now,
5.
already.
Your audio is audible here. Please mute yourself.
நீ எதுவும் செய்யல அவ்வளவுதான்
Sorry. Sorry guys. So let's see. X minus x cube plus 5x square minus 8x plus 4. First we have minus x square minus x cube minus become plus x square. This get cancelled, and here we have 4 square minus 8x. So we should go about 4, then it will become 4x square minus 4x. So here we have minus 4x only, and plus 4 comes down. So we have this time minus 4x plus 4, and we have successful 0. So we get factorization like this: x minus 1, and here you have minus x square plus 4x minus 4. Okay, and what it is? Minus of x minus 1, x minus 2, x minus 2, yeah, whole square. So you see, this is characteristic polynomial, and because minimal polynomial has same root, so there should be root minus 1 and minus 2. Sorry, there should be root 1 and 2 here. All the roots should be set of all the roots matches in minimal polynomial and characteristic polynomial. But it does not set with first of P does not satisfy say. So this is not a minimal polynomial. So after degree 2, there is if you go higher degree, so degree 3 comes. But 3 degrees characteristic polynomial, that should be same as minimal polynomial also. So this is good. Option B is correct. Now, what about third option? C. Is R3 direct sum of W1 and W2? W1 and W2. Direct sum of W1 and W2. Can it happen?
Yes, sir.
How? Do you see what? Kernel of T1? Any relation between kernel of T1 and kernel of T2, which is annihilated by T1 will be annihilated by T2. So this is correct. This option. Is this relation understood?
No, sir. Please
Please
repeat
explain,
it.
sir. Please explain,
Something
sir.
with okay. Let me write down here. We have very uh, short page left, but we'll solve here. Something which is annihilated by T1, let's say T of x is equal to 0, this will imply T1 square of x is equal to 0, correct? So x belonging to kernel T1, this will imply uh, x belongs to kernel T1 square, right? If you see it, T1 and T2, what can you say about them? T2 is nothing but T1 square, right? So kernel of first T means T1 is contained in kernel of T2. But uh, then, then this direct sum is not well defined, right? W1 and intersection W2 will be what? W1, because W1, this is W1 and this is W2. इंटरसेक्शन में तो W2 sorry W1 आ जा रहा है and W1 is non-zero. That is important because this matrix this matrix T minus 2i, it is written here for T1. This matrix is non-zero matrix, okay, and it is not invertible because 2 is an eigenvalue. It is not invertible, then W1 is non-zero. There is something inside kernel, some eigenvector corresponding to 2. So
Sir,
intersection is W. Okay.
sir, how can we say that t minus 2i is not invertible? What is the theory behind this?
What is
How to find
definition
out
for
W1, W2, W3, all this, please.
W1, W2, W3 at this definition? This is just kernel of T1. Now what is T1? T1 is written.
Uh, uh,
This is kernel of T2.
uh,
Right? This is kernel of T4. Okay, so someone asking why, let me stop here this work. So why T minus 2i is not invertible? If it was invertible, because 2 is an eigenvalue, correct? Sorry, 2 is an eigenvalue, right? Look at this description. So there exists some non-zero v, which is called eigenvector. V is non-zero. So something belongs inside. So you know one theorem which I mentioned many times, and inside class also it was discussed. Some t is invertible, t is invertible, or even 1 when kernel of T is just trivial element. Nothing else comes inside kernel. But we have kernel non-zero V here. So T minus. So apply this theorem. This says T minus 2I is not invertible. Okay. So there is something inside the kernel. So this direct sum is not defined because W1 is contained in W2 and W1 is non-zero. So some non-zero elements come inside intersection. This is not even defined in direct sum. What about the D part?
Please write down the two words, sir. Just you are
Right?
repeating. Just you are telling that one you must. Please write.
Okay. Let's see. Since W1 is contained in W2 uh, and W1 is non-zero, uh,
I
W1
think
direct.
W1 is subspace of W2.
Okay. Here we have question marks. Some one is contained in the other. That is all.
Exactly, sir. So W1 is common.
So something is common. So this is not well defined. This is not well defined. This direct sum is not well defined. And this is if it was linear sum, I can understand situation. But while saying direct sum, you should not have any non-zero intersection. Okay, intersection can happen only at zero element. W1 is inside W2.
Yes, sir.
Whoever
Intersection should
was
be singleton zero.
if it was direct sum then. So let's see part D. What was part D? Part D says direct sum of W2 and W3 they span R3. Okay. What is W2? W2 is a generalized eigenspace of eigenvalue 2. Okay. Kernel of this T2 and W3 is eigenspace corresponding to eigenvalue 1 because kernel of T minus I is just eigenspace. And this is generalized eigenspace for eigenvalue 2. So they are linearly independent. There is no element common, that is for sure. Something which is annihilated by T minus 2I that cannot be annihilated by T minus I because eigenspaces are linearly independent, right? Hmm. Okay. So
D is correct, sir.
this seems to be correct because there is no intersection, but we should understand first what is nullity of T2 and nullity of T3. If sum is 3, then we are done. Okay. So this is correct if nullities, sum of nullities is 3. Means dimension of W2 plus dimension of this is explanation for D. W
Sir,
yes.
here, as you said that W2 is the generalized eigenspace and W3 is the generalized eigenspace, then what is the
No.
requirement of seeing this, the sum of range? So the sum of nullity is 3.
Okay. This was motivation was given before the lectures, but let me explain once more. This I did not given the motivation. It was given in the class. Okay. So don't worry. I didn't say anything. So when we say operator is diagonalizable, what we have there we have uh, that V is coming out direct sum of eigenspaces. right? First theorem. V is direct sum of Wi's. Means we are just given any operator, we are thinking of uh, dividing, dividing, factorizing V into simplest form, some key invariant subspaces. Okay, what diagonal matrices do? They actually find a basis of invariant subspaces. Sorry, invariant lines, I would say, because every vector, eigenvector, that itself uh, is an spanning invariant subspace. Okay, so in diagonalizable things, it was clear, but now we are handling with general operators, and there we don't have enough eigenvalues and eigenvectors. What we do, if in case primary decomposition, this is nothing but primary decomposition theorem. Okay, oh, D follows from primary decomposition theorem. No need to write anything. D follows from primary decomposition theorem. Decomposition theorem says that you might not be getting V as direct sum of eigenspaces, okay, but you can get direct sum of if minimal polynomial factorizes into linear factors like this, okay, some pi power ri, like this, minimal polynomial factors like this, then you have, by primary decomposition theorem, you have that V is equal to direct sum of generalized eigenspaces. Okay, means kernel of P I R I T. Direct sum of these things, V comes out to be this. Okay, so here we have P1 is equal to this and P2 is equal to this. P1 is equal to x minus 1 and P2 is equal to x minus 1, P2 power 2, P2 power R2, you get x minus 1 power. So, by primary decomposition theorem, you decompose V like this, direct sum I belonging to some index z, finite index x. So this is how the motivation comes. You want to decompose V into simpler form, means direct sum of T invariant subspaces. Okay, because then you can restrict your operators into uh, invariant subspaces, and now they are in lesser, in some sense, like lesser in dimension. So if you want to study something which is in bigger dimension, you want to break them into simpler pieces. Okay, that is what the motivation comes. Diagonalization was first step, was simplest form, but if diagonalization may not happen, some cases like you may not have enough eigenvalues or eigenvectors, but in this case where P minimal polynomial factorizes like this, then we have this primary decomposition theorem, which says we can be decomposed into these things. Okay, okay, so I suppose everyone understood this, right?
Sir,
So, okay,
you please write the theory behind the option D because even it is not clear to me.
was said inside the classroom when decomposition is started. Okay, you can watch 10 minutes. Professor clearly explained this because I don't want to practice.
The
Okay, sir.
professors has given more importance on theory, sir. The
That is
problems,
what I am also
if we
pointing
discuss
out the same.
parallel problems, then we will understand more the theory part.
So, I'm doing problems only. So I was giving motivation that why we need decomposition and these things. if you have bigger vector space, you want to break them into simpler pieces, huh? So that you can restrict your operators into it. So you want decomposition in such a way that all wi's are basically T invariant. That is the main point. So, but anyway, you understood this B part, right? If you
Sir,
not understood, what?
sir,
Tell me.
A is the zero matrices. A is the 3 by 3 zero matrices. Also, A is the zero matrices. Also, B is correct, sir.
B is correct because B satisfies T. You know,
Okay, sir.
What is P? P is characteristic polynomial as well as minimal polynomial also.
Yes, sir.
Okay.
A is satisfying the 3 by 3 zero matrices. If A is the zero matrices, B is also correct, sir.
No, no, no. For that, minimal polynomial is just x, and characteristic polynomial is x cube. So that does not matter matches. Here we have particularly A equal to this. Okay, we
Okay.
calculated eigen value, characteristic equation, and all this. So, but D, what about D? Focusing into D, I'm applying just a primary decomposition theorem. Okay, so we
Okay,
have
sir.
decomposition like this, but here we have V is equal to direct sum of, first let me write, kernel of P1T. P1T is P minus I only. With direct sum, what is P2? Kernel of P minus 2I square. Okay, but what is this kernel of? This is nothing but T1. This was T1, right? No, no, no. T minus I is T3. This was T minus I is T3. And what is T minus 2I to the whole square? T2.
T2.
Okay. This is T2. Now what is kernel of T3? This is W3. What is kernel of T2? This is W2. We just direct sum into uh, W2 and W3. This is correct. Okay. I clearly explained part D also. You can look into my video once more if you wish. Twice, thrice speed, whatever. So let's see question 5. Will be R5 to R5 a linear operator. Rank of T is 1. Rank of T is 1 means matrix representation. In matrix representation, only one row or one column is non-zero. Okay. Or one column is multiple of, means every column is multiple of one column. Particular. So but here, if P is diagonalizable, can T be nilpotent? Not necessarily.
Sir, please write the reason, sir, why it is not.
If this is diagonalizable, any power, take any power, it will be same for every R. This says A is not nilpotent. This is diagonal matrix in fact, but it's not. Why I'm saying necessarily, because take 0 0, it's one power only becomes 0 0. But this is some saying that it is incorrect. Not necessarily is enough. Giving a counter example is enough. I'm saying. Okay, so this is incorrect. Diagonal matrix may not be nilpotent.
Nilpotent means?
Some power becomes 0. Let me
Okay.
write nilpotent. Some T V to V is nilpotent if some composition is 0 or some are in 1. Okay. What about second option? Can someone point out P is diagonal eligible, then P cannot be nilpotent. Let's say we are defining diagonal eligible, matlab in the diagonal we have non-zero entries. Okay, this is convention. Okay, by convention, then it cannot be nilpotent. Look at this. Any diagonal matrix is, let's say, lambda 1, lambda 2, take any power. What it will become? Lambda 1 power r. Some non-zero entries are given here, lambda a power r. And this will be again the diagonal matrix, non-zero diagonal matrix. Okay? So it cannot be nilpotent. Yeah. We are understood like this. If some lambda I is non-zero. So this is explanation for part B, and this is correct. Cannot be nilpotent. In some lambda, let's say lambda 1 is non-zero, then any power of lambda 1 will be non-zero. So it is again diagonal matrix. It is not zero, so not nilpotent. So if T is nilpotent, then T cannot be diagonalizable. What about this? This is good. How to solve this?
Sir, I have a doubt.
What?
Can we say that every invertible matrix is not nilpotent?
Yes, because if T is nilpotent, let's say T square is equal to 0, means T power something is 0, then we have, sorry, determinant of T. What is determinant of T? This will be 0, right? Because T power, determinant of T power R will imply, 0 will imply determinant of T will be 0. But this will imply T is not invertible. But you are taken, is in its starting, you have taken T invertible. So it cannot happen. This is counter example. Means, sorry, contradiction. Given T invertible, and if you assume and T power R becomes 0 for some R, then we have problem here. Determinant 0 implies T is not invertible, right? Okay. So your point was correct. This is good intuition.
Sir, so we can say that option C is correct using these theories.
If P is nilpotent, then it cannot be diagonal eligible. It's something T something non-zero and nilpotent. Okay, we are always taking non-zero. T is non-zero. Correct. So T is non-zero and nilpotent. So what is minimal polynomial for T? What is the part C? Minimal polynomial of T is x power r, some r, some r. Okay. We have taken non-zero everywhere. T is non-zero. Otherwise, there will be some problem. Zero case. That is trivial case. Okay. So what is eigenvalue? Eigenvalue of T is nothing but zero only, right? Zero, 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 all zeros. Means then If it is, we want to show diagonal as well, algebraic multiplicity and geometric multiplicity, they should match.
Both are same.
Both are same, you are saying.
Yes, sir.
Not
Algebraic and geometric multiplicity are same, then diagonal algebra.
correct. But what is kernel of t here? Kernel of t minus 0, I. This is geometric multiplicity, gm of 0. Means dimension of this. But this is nothing but dimension of kernel t only. If t was non-zero, what is kernel? This is some w, which is a fixed subspace of V. So eigenspace, you have only one eigenspace. We had taken, we had taken T non-zero. So kernel of T will be some proper subspace. So what can you say? Eigenspace span of eigenspaces is not equal to V. This implies T is not diagonal. So
Sir,
what
what is the significance of the rank of T is 1?
rank of T is equal to 1, there is no significant in fact. The thing is that the image of T, since T is mapped from V1 to V2, is contained in, means that image is explicit exactly one dimensional subspace. Okay, means that the line passing through 0 0 means origin, yeah, passing through identity of the vector space. Think
Sir,
the image is just line. What?
for the option C, can we proceed like this? In the we assume first that T is nilpotent, and we suppose that T is diagonalizable. Then it is
Okay,
then T is equal to P inverse D P1 for some
okay,
invertible P.
okay,
Then after, as a T is nilpotent, then for there exists at least some K for which to the power K is equal to 0. And if we multiply
yes,
T, then it becomes P inverse D,
correct,
P, P inverse D, and but right hand side becomes 0 if we take determinant. Sorry, left
yes.
hand side becomes
P
0
power
and
r
right hand side
P
non-zero.
inverse D power r P. But this, if P power r becomes 0, this will imply that D power r becomes 0, and this will imply that D is itself 0. So, so the operator T is itself 0. This implies T is 0 operator. Nothing else can be similar to 0 operator. 0 operator is unique. So this is also good. If T is non-zero, I sort by counter means contradiction, that eigenspace of T cannot span V, so T is not diagonal. You also sort if T is nilpotent non-zero, if T is nilpotent and T non-zero, then we got contradiction here again. So only 0 is nilpotent and diagonal. This is not diagonal. I don't like that because 0 is some trivial case. We are talking about non-zero things. So in that case, your
But,
but
but sir, in the question, it is not given that tree is non-trivial. It may be sometime trivial.
if T is 0, it is nilpotent as well as diagonalizable. If you say if it is
Yes,
diagonal matrix, huh?
yes,
So,
sir.
so if it is not given correctly, you can raise your point. But for time being, I am let me make it's clear that T is non-zero. Okay, in every option, T non-zero things are given. And this is incorrect. So this T part is anyway incorrect because B is correct.
Sir, C part is also correct now because here we assume the
Oh,
T is more important
sorry.
and then T are diagnosable.
Correct. My fault. This statement is correct. Good. Thank you for cooperation solving with me. Let's see sixth question. We have enough time right now. Yes. How much time we left? Okay, we have 15 more minutes. We have to solve quickly. Let's see 4 cross 4 matrix A. Rank is given 2, and this is given from this equation. If you say A cube is equal to A square, you get A cube minus A square is equal to 0. This implies A satisfies this equation. Minimal polynomial divides x cube minus x square. Okay, and it is given that A square is not 0. So from A square is not 0 is given here. Okay, so here you have A square A minus I is equal to 0. So minimal polynomial divides this means x cube. This is equal to x square outside. This is x minus 1. So what can be minimal polynomial? Minimal polynomial has choice either x minus 1 or x square x minus 1. Can this happen? First observation. If first happens, what will happen? A minus 1 is equal to 0. This will imply A square is equal to A. This implies that A is projection map, right? So what is matrix representation of A? Something like 1 1 0 0 here. If it happens, stuff happens. Sorry. So this will imply this, and this is diagonal eligible. It is contradiction because not diagonal eligible is given. Let's say like this. Okay. So minimal polynomial for minimal polynomial. So minimal polynomial is x square x minus 1. Okay. Okay. So there is the Jordan block like this 2 cross 2 because this minimal polynomial we have 0 vector x minus 0 has power 2. There is block like this Jordan block. Correct. What about the second option? This fails because once it happens a square is equal to a, it is projection operator and projection operators are diagonal eligible. Okay, so this is incorrect. There exists a b non-zero such that a b non-zero but a square b is 0. Yeah, this is good and this is correct. This is correct because kernel of a is Because rank is 2, this implies nullity is also 2. Nullity of A is 2. So there is something inside kernel. So kernel is two-dimensional space. But from here you observe this x minus 1 does not satisfy say, means this is non-zero, means is not minimal polynomial, is not minimal polynomial. This implies a minus 1 is not 0. So there exists b inside b such that a minus 1, a minus I is a non-zero operator. So there is something which is non-zero. Means we apply to b, this is b, it is non-zero because this operator is non-zero. So it got something which is sending in non-zero, sending to non-zero. So, but now if you apply a once more to this vector, this is non-zero vector a minus I apply to b, this will become 0 because this is nothing but a square a minus I. Now it is 0. Apply to anything, you will get 0. This was this non-zero vector. So this is explanation for part C. And C is correct. Characteristic polynomial of a is x power 4 minus x. Incorrect. This is also false. You know why? Because minimal polynomial satisfies this equation. X minus 1, x square x minus 1. Can it divide characteristic polynomial x power 4 minus x? It can never divide because this has factorization x into x cube minus 1. And here you have power 2 of x. Here you have power 1. Right? So this does not divide. So this is not characteristic polynomial. This is not characteristic polynomial. D part is also failing. So let's see next question. Question number 7. Okay. You have this matrix A and B. What about B is similar to A? I'm saying B is similar to A. Because B is Jordan canonical form of A. What is minimal polynomial for this A? X minus 2, x minus 3. If you subtract 2 from the diagonal, it is still, its rank is, its square is not 0. It is not 0, but its square will be complete. So this is your minimal polynomial as well as characteristic polynomial of A. So write Jordan form for A. So you will get this block, first block, because you have minimal polynomial x minus 2 power 2. This 2.
Sir, please write the reason, sir.
Reason for what? Minimal polynomial.
No. For this,
Calculating
no. Reason for this truthness. True means right, false means right. So that we can understand.
Okay, ठीक है. So A is is not similar. This is incorrect because B is nothing but Jordan canonical form of, means similar to Jordan canonical form of A. So this is B is nothing but similar matrix to A. So this is what there is this data. You can write Jordan canonical form. It is unique matrix coming out like this. You will get for 3. You will get, because it is power 1. you will get 1 cross 1 block. For 2, you will get 2 cross 2 block, and no extra block will come. That is why it is unique. No extra block will come because we got some of the orders equal to 3. If extra block comes, some bigger vector space will take the place. But we won't go to bigger than R3. So these operators are in R3. So that is why. So what about B option? A is diagonal is over the field of Western number. No. Algebraic multiplicity and for 3, symmetric multiplicity for 3, which is eigenvalue, is 1. This is very well nice, but for 2 there is some mistake. Algebraic multiplicity of 2 is 2 because characteristic polynomial has power 2 in the factor x minus 2. But what is geometric multiplicity? This is 1. Let me explain why. If you subtract 2 from the diagonal, you will get 0, 0, and here you will get 1, 0, 0, 0, 0. You already had 0 here. This is bigger 0. But left in upper triangle, 2, 1, minus 1. 2, 1, minus 1. This is your t minus 2i. What is nullity? Means dimension of kernel t minus 2i. This is nullity of t minus 2i. Because rank of this matrix is 2, right? 2 non-zero columns. Yes, 2 linearly independent columns. So this is 3 minus 2. This is just 1. Rank nullity theorem I'm using because rank is 2. So we got that option B is also false, right? Diagonalizable means algebraic multiplicity for every eigenvalue corresponding to geometric multiplicities, they are same. So B is Jordan canonical form of it. This is correct. We just saw this from here. This data will imply this is part explanation for part C. Characteristic polynomial of A and B are same, but minimal polynomials are not same. This is incorrect. Similar matrices have same characteristic polynomial and same minimal polynomial.
The reason
This
for
is the
C, sir.
reason for C is given here in the box. Minimal
Oh,
polynomial for A and characteristic polynomial for A are same. And once you write Jordan canonical form for A, you will get uniquely B.
okay, sir.
No other possibility there. No other possibility. And so let's see next question. We are very slow today, I think. Anyway, let T be linear operator from R7 to R7. Matrix representation of T is given by A. B is standard ordered basis. W1 be null space of this vector. W2 be this null space. W3 be this null space. Where V is direct sum of these Wi's. The minimal polynomial for T is given by this. Which of the following is correct this statement? First of all, write Jordan canonical form. That will be the very helpful. Can it happen? Geometric multiplicity of eigenvalue 1 is 3? Not necessarily. Look at this matrix. Okay. Which matrix? I'm writing here. 2, 3, and 1. 2, 1, 2, 0. This is your first block. Second block, you write 3, 1, 3, 0. You can write once more 3. There is no problem at all. Now
How
you
you
write
are
1,
writing
1.
this first block, sir? 2, 1,
What?
0, 2. How
2,
are you
1.
writing this first block? 2, 1, 0, 2. How are you writing this?
This is Jordan block corresponding to eigenvalue. This was definition of block. Diagonal will be lambda and super diagonal entries are 1. That's all.
Okay.
So
Eigenvalue
minimal
2.
2 cross 2. Why it is 2 cross 2? Because in the minimal polynomial we have this power 2.
Oh. Okay.
Why 3 comes in 2 cross 2? Because minimal polynomial has power 2. Now
Okay.
any other things which comes are 1 cross 1. That's all. So this is one possible matrix. And this says geometric multiplicity of 1 is what?
2.
I kernel of t minus I. Dimension of kernel of t. This is 5. In this case, it can never be 3. Never. Not necessarily. Never. Because you see, only these are possible for places of 1. What is left outside? That will be always in the kernel of t minus I. This is bigger than or
Sir,
equal to 4 because of first two blocks. First two blocks. So
sir, I have a
that
doubt.
means yes. Speak.
Sir, here in the place of 3, we can also write 1. Then the geometric multiplicity will become 3.
No. Geometric multiplicity is dimension of kernel of t minus I. Once you subtract I from this matrix, these 3 entries will become 0,
Hmm.
and then kernel will be, oh my god, sorry, kernel will be of 3 dimensional. Sorry, this is mistake. My mistake. Sorry. Then rank will be 4, and kernel will be 3 dimensional. You are correct. My computer will stop. So this is not necessarily true. Okay. Sometimes it can be true that someone was pointing out right now. Sometimes it can happen true, but in this case we are failing. And all the condition, if you see in the hypothesis of the question, all the conditions are satisfied here. All the conditions of the question are satisfied. Satisfied. So, but we are failing. Geometric multiplicity is nothing but 2. As this is dimension of kernel of t minus I. If you subtract in the diagonal by 1, you will get 5 non-zero entry in the diagonal. So rank will be 5 and the kernel will be 2. Okay, so A fails. Now what left is, oh, this is primary decomposition theorem itself. restriction operator has minimal polynomial by this. P1 correspond to W1 correspond to this a minus 2I power 2. Okay, so second option is correct. This is primary decomposition theorem. Restriction operator have correspondingly Pi power Ri will be the minimal polynomial for Pi, right? From that. About other things, they are zero. Sorry, they are incorrect. They are incorrect. I'm writing here. Minimal polynomial for P2 is nothing but x minus 2 whole square. Minimal polynomial for these are all coming from PDT, primary decomposition theorem. T3 is equal to a minus I is x minus 1. Minimal polynomial for T4. Sorry. Yeah, that's all. That's all right. This is only needed. Was minimal polynomial for T2 will be uh, restriction of W a minus 3I whole square. So here we do not have a square here, na? That is why we are failing. Okay. So if it T2 x minus 3 square, and here we have just x minus 3, that is why it is wrong. Okay, so let's see next question. How much time we have? Oh, sorry, we have crossed the time limit. Can we have 5 more minutes?
Definitely, sir. Definitely.
Yes, sir. Yes, continue, please.
Thank you. Let's see question 9 here. Only 2 questions are left. Sorry for A is this matrix and W is this null space of A plus I. W and this description null space of A minus 2I where projection operators even E2 E3 are projection operators. Wi are corresponding range spaces. Then which of the following are incorrect? What W and W2? Focus on W and W3. See, while primary decomposition theorem, you got D operator, which was saying if you have x minus c k, sorry, lambda minus x minus c k, if your minimal polynomial is something like c k power r k, then this c I e I, this sum, this was similar to diagonal matrix, right? And then there was this p minus d, which was defined like n. N was becoming nilpotent matrix. This was px means minimal polynomial product of these things or rk is k, and this is r2. Then n power r is equal to 0 for r bigger than ris, r every I. Anyway, so this was just to recall things. A minus 2I. What is a minus 2I? 0, 0, 0, 0. Sorry, 1, 0, 0, 0, 0, minus 3. What is for this kernel of this matrix? 0, 1, 0. Okay, this is span. 0, 1, 0 is only thing which is going to 0. Okay. By looking at this, you see where E1 goes to E2. Where E2 goes, this goes to 0. Where E3 goes to -3, E3, -3, E3. Yes. So what kernel is generated by just E2. So write for W3 or W2. For W2, what we have? A minus 2i. This was for W2. W1 क्या है? W1 is span A plus I means we have 3 0 0 1 3 0 0 0 0. Look at it. What E1 goes to 3 E1 plus E2. E2 goes to 3 E2 and E3 goes to 0. So what is kernel? Sorry, this was kernel for this matrix. Kernel. This is kernel of this matrix, and this is spanned by E3. So E1, sorry, E2 plus E3. This is not R3. So what? This option is incorrect. Right. Sorry, we want to choose incorrect things. This is correct. Everything else is actually correct. E minus P is nilpotent of. This follows from this description which I was telling. After primary decomposition, uh, the- there was this description. So this is correct. But as an option, it is false. This is false. This will be also false. Okay? And look at here. It was nothing but. It is actually nothing but eigenspace corresponding to 1. This is kernel of P minus I, sorry, T plus I, and this is kernel of P minus uh, kernel of P minus 2 I square, and these two are eigenspaces, so they are mutually independent. So direct sum will be R3.
Sir,
Yes,
I think option B is the relation given in the option B is also wrong, because if we take A minus 2i, then the matrix is 0 0 0 0 0 0, and the last entry is 1. Then the null space is generated by E1 and E2. And
correct.
if
So this is generated by E1 and E2. Correct. You are right.
E2
Now
and
and
W1 is generated,
by E3.
one is generated by, no sir,
Here it
I
is
think
written.
by 2, E2.
W1 is spanned by E3. Written
Oh,
here. Here you see. So yes, this is pretty much good. W1 is spanned by E3 and W3 is spanned by E1 E2. So the direct sum is R3. So this is correct statement. So this is failed because we are choosing incorrect statement. So let's see last question and go for dinner. Okay. B is a space of polynomials of degree less than equal to 3. Differentiation operator on it. Maybe the matrix representation.
Sir,
So
last question, B is the correct or incorrect, sir?
B is statement is correct, but we are choosing incorrect things. Na? Only first is incorrect. This is incorrect.
Remaining 3 is the okay.
Correct.
Oh, incorrect.
Remaining three are
Remaining three
correct.
are correct, but we need to choose incorrect.
Incorrect. Correct.
Yes.
Correct. Okay, sir.
Okay, sir. Okay, sir. B, C, D
Okay.
are the correct statements.
Yes. Everything else is
Okay, sir.
correct option.
Okay.
So
Okay,
this
sir.
was the description where before primary decomposition it was shown na, that D is equal to D is defined like this: Ci Ei, sum of Ci Ei. Then D is diagonal, obviously diagonal matrix. You can check it. And P minus D was nilpotent matrix. So you can find it out there. But anyway, let's see 10th question. Let write matrix representation for it. A of 1 is differentiation operator. It will become 0. Is of x. I'm operating on a standard basis. This will become 1. A of x square. This is 2x. A of x cube. You get 3x square. So matrix representation for A is nothing but first will be 0, 0, 0, 0. Because this is summation 0 into basis 1x power I from 1 to 0 to 0 to 3. Now what is it? This is 0 in, sorry, 1 into 1 and everything else is 0. 0 into x plus 0 into x square plus 0 into x cube. So you get 1, 0, 0, 0. Write it like the same thing. So you get here 0 into 1 plus 2 into x plus 0 into x square plus 0 x cube. So you get 0, 2, 0, 0. And similarly you get 3 here and 0 here. So rank of A is 2. Galat. You see, there are 3 non-zero rows, right? Linearly independent rows. Okay. These rows are mutually independent. So no one can be obtained from any two. So A is diagonal as well. This is failing because A is nilpotent. Of order 3. Yes. Square, cube, 4. Order 4. But order 4. A is nilpotent, yes. Jordan canonical form for A is, see, minimal polynomial for A. Minimal polynomial for A. This is x or 4. Okay. Once you have, sorry. Minimal polynomial is just x and characteristic polynomial is, no. Characteristic polynomial, minimal polynomial, they are same. Sorry. If it was x, it matrix would have been 0. Okay. So you have x power 4 in. So there should be a 4 cross 4 block, correct? With 4 cross 4 block with eigenvalue 0. So diagonal should be 0 and super diagonal should be 1. So this is correct. Last option is correct. You understood this? There should be a 4 cross 4 block. Now no other option. 4 is completed because dimension of V is what? Dimension of V is itself 4. So no need to search for any other eigenvalue or other block. So the unique block you get is this. Matrix representation, once you have the rank of A is 2, this is false because rank of A is actually 3. Okay. This is you check, verify. This is easy. This super diagonal go more super. Next will be coming here, and next to next will come here, and next time it will become 0. This is in the first option. If you take power 1, you get non-zero entries here. If you take power 2, non-zero get entries are here in this. If you take power 3, non-zero entries are here. If you take power 4, non-zero entries, there is no, means all entries are become 0. So x power 4 will become 0. Anyway, this is the explanation. If you wish, you can watch it once more. Okay, I'm stopping recording.